We present a fully passive method for high-resolution facial performance capture. For the first time, our method requires no markers, no face paint, no fluorescent makeup, no structured light, and no laser scan models, yet still we are able to automatically reconstruct time-varying meshes with 500,000 vertices at 30 frames per second. We also reconstruct high-resolution time-varying texture maps for high-quality rendering. Here's an overview of our method. Our capture setup consists of 14 high-definition video cameras arranged in 7 binocular pairs. Each pair is zoomed in to capture a small region of the face in high detail. We use binocular stereo to reconstruct each of the 7 surface regions independently and then combine them into a single high-resolution mesh for each frame. We then consistently track geometry and texture over time using an optical flow-based technique with automatic drift correction. Our setup consists of a camera array with bright LED lights to provide uniform illumination. We divide the face into 7 overlapping regions and arrange the cameras in 7 corresponding stereo pairs. We optically increase the zoom level of the cameras so that we observe fine-scale surface details, providing a natural surface texture for reconstruction consisting of skin pores, blemishes, and hair follicles. Here we see a full-resolution image from one camera. We perform iterative binocular stereo to reconstruct each frame as described in the paper. Here we see the initial reconstructions for one of our capture sequences. The zoomed-in cameras allow us to use skin pores, hair follicles, and blemishes as surface texture to guide the stereo algorithm, producing detailed initial meshes with roughly 1 million polygons each. Given the per-frame initial meshes, we then reconstruct the motion of the face by tracking the geometry and texture over time. We wish to explicitly compute a sequence of compatible meshes without holes and per-frame texture maps for creating high-quality renderings. We propose an optical flow-based method that starts with a neutral expression reference mesh generated from one frame. A high-resolution texture is then computed from the video images. The observed pores and other surface details not only serve to provide accurate per-frame reconstructions, but also allow us to compute dense optical flow between video frames. We use the flow combined with the initial reconstructions to automatically propagate the reference mesh through time, computing per-frame textures as we go. Tracking drift caused by inevitable optical flow error is automatically detected in the per-frame texture maps and corrected in the geometry. We also incorporate edge-based mouth tracking since optical flow is prone to errors during rapid deformations such as lip movement when speaking. The details of our method can be found in the paper. Here is the resulting geometry from the sequence we showed earlier. The output is a set of compatible meshes that have the same connectivity and an explicit vertex correspondence, essentially one mesh deforming over time. We can visualize the face motion using a static checkerboard texture. Notice how the skin stretches and compresses during deformation. The stability of the checker pattern indicates a drift-free reconstruction. And here is the final high-quality rendering for the sequence using the per-frame texture maps. The compatible mesh sequence allows us to add virtual makeup to the face. An artist would edit the face in only one frame, and we can propagate the edits over time automatically. Notice how the virtual logos here naturally deform with the face motion. We now show other facial performances captured with our technique. Once we have the final geometry and textures, we can render from any viewpoint or change the scene lighting. We have presented high-resolution passive facial performance capture. To our knowledge, the first fully automatic technique to achieve high-quality results without the need for markers, face paint, or structured light.